Welcome viewers. So, we are continuing with the same topic, that is the spectroscopic methods. So, under this topic we have already discussed NMR spectroscopy, UV visible spectroscopy and IR spectroscopy. Now, I will be discussing the next technique, which is the flame photometry. So, to start with this technique, let us take a quick look at the lecture plan. I will be covering the different topics, which includes introduction of flame photometry, the principles of flame photometry, chemical reactions which takes place in flame, ionization in flames, spectra of metal in flame, effect of organic solvent on flame spectra, then the instrumentation of the flame photometry and applications of flame photometry, and in the end we will be discussing the advantages and the disadvantages of the technique flame photometry. So, coming on to the introduction of the technique flame photometry. It is a branch of spectroscopy where species in the form of atoms are examined in the spectrometer. Here excitation is caused by spraying a solution of the sample in a hot flame. It is concerned with the emission of characteristic radiation in flames by individual elements and the correlation of the emission intensity with the concentration of the element introduced in the flame. It is based on measurement of intensity of the light emitted when a metal is introduced into the flame. The wavelength of the color tells what the element is, and the intensity of the color tells the amount of element present. So, we can get both the information, type of element and the amount of element present in the sample. However, the efficiency of forming excited atoms in the flame is low because other processes like formation of molecular species, incomplete vaporization, incomplete excitation decreases the emission intensity of the atoms. Following phenomena occurs when a sample is sprayed into the flame. Number 1, evaporation of the solvent takes place, leaving a solid residue. Number 2, vaporization of the solid with dissociation into its constituent atoms, which are initially in the ground state, are obtained. Number 3, excitement of some atoms by the thermal energy into higher energy levels. Number 4, the excited atoms then emit radiation characteristic of their species. Number 5, the emission spectra consist of line originating from the excited atoms or ions. The neutral atom spectra are of main interest in flame photometry. Spectra are produced at high temperature and high concentration of the atoms in the flame. That means, we have to provide high concentration of the atoms in the flame to obtain a proper spectra. The energy emitted during the transition is, this is basically the energy difference E2 minus E1, where E2 is the energy of the higher level and E1 is the energy of the lower level. This is equal to h nu, where h is the Planck's constant and nu is the frequency. So, E2 minus E1 is equal to hc upon lambda, because nu is equal to c upon lambda. So, substituting the value of nu, we have hc upon lambda. So, from here we can obtain the value of the wavelength lambda, which is equal to hc upon the energy difference E2 minus E1. The wavelength is a characteristic of the element, as I have already told, and intensity of the radiation corresponds to the amount of element which is present in the flame. The temperature of the flame in flame photometry lies between 1000 to 3000 degrees Celsius. So, coming on to the principle of flame photometry. So, we can see from this figure, we have liquid sample containing element is aspirated into the flame. We have mx. Now, this is converted into the mist. Now, this gets evaporated and the evaporation of droplets takes place. Now, on evaporation, a solid is formed which on further vaporization changes into gas. This gas undergoes dissociation and the molecule it gets dissociated into the various components, like we have M plus X. Now, this M, this is the metal part, this on thermal excitation this gets converted into M star, which emits H nu, the amount of energy H nu. This is detected by the flame emission. So, we can detect it by the flame photometry. The second process is this metal M, this undergoes absorption of radiant energy H nu, and again M star is formed, and here re-emission takes place, which we study under the technique fluorescence. A fraction of neutral atoms or radicals formed in the flame combine to form a new gaseous compound. Fraction of free atoms which are thermally excited is governed by Boltzmann distribution law, according to which N star upon N naught is equal to G star upon G naught into e to the power minus delta E upon k T, where N star is the number of atoms in excited state, N naught is the number of atoms in ground state. The ratio G star upon G naught is the ratio of statistical weight for ground and the excited state. Delta E is the energy of the excitation, K is the Boltzmann constant, and T is the temperature in Kelvin. The most favorable condition for the flame photometry is high temperature and low excitation energy. Calculation shows that only a small fraction of molecules gets excited even on getting the most favorable condition. Elements whose resonance lines are associated with higher energy values are more sensitive. Example, alkali and alkaline earth metals. Flame absorption spectroscopy, it depends upon the particles which are electronically excited in the flame, and the flame emission spectroscopy. It is based on the particles that are present in the ground state in the flame. So, this is the difference between the flame absorption spectroscopy and the flame emission spectroscopy. Coming on to the function of the flame. Number 1, conversion of liquid constituent into vapors. Number 2, decomposition of the constituents into atoms. Now, the vapors they undergo dissociation into atoms. Number 3, electronically excitation of atoms and molecules to produce the spectra. Usually high temperature enhances emission intensity and provide greater sensitivity, but in some case low temperature is advantageous. Analysis of alkali metals is carried at low temperature because the high temperature, that means at high temperature other elements also interfere. So, alkali metals they are analyzed at low temperature. Coming on to the chemical reactions which takes place in flame. First is the initiation process. In initiation process, the dissociation of two atoms take place. As we have hydrogen, this is the hydrogen molecule H2. When heat is provided or this is heated, it is dissociated into H radical. So, two H radicals are formed. Similarly, in case of oxygen, on heating two O radicals, oxygen radicals are formed. Next is the chain reaction. In chain reaction, a hydrogen radical which was formed earlier, it reacts with oxygen molecule and an oxygen radical plus HO radical are formed. The second option can be the O radical, it reacts with H2 molecule to form H radical plus HO radical. The other option can be H radical, it reacts with water molecule to form H2 hydrogen plus HO radical. Here the excess energy is transferred from one species to another. So, this is a chain reaction and it keeps on continuing. Energy is only released on collision with a third body, as for example KCl. So, we have H radical plus KCl, these two combine and they form K free radical plus HCl, or two radicals they can combine together like H free radical plus OH free radical plus KCl, they form water plus K free radical and Cl free radical. Next is the excitement of the metal atom. Now, the K, the metal atom, on heating it transforms to K free radical. Emission of characteristic radiation by the excited atom. Here the K free radical, it emits a particular radiation H nu. Due to ionization of metal at high temperature, following equilibria exist in flame. This is the metal, this is in equilibrium with M positive plus the electron, and the equilibrium constant for this equation is K. K is the equilibrium constant. This is given by the concentration of the product upon the concentration of the reactant. So, in this case we have product M positive plus electron. So, the concentration of M positive into the concentration of electron upon the concentration of the reactant, which is the metal M, and this is equal to alpha square upon 1 minus alpha minus P, where alpha is the fraction of metal capital M and P is the partial pressure of the metal before ionization in the gaseous solvent. At high temperature, greater fraction of atoms gets activated. According to Shah equation, this is the equation where the variation of K, that is the equilibrium constant with temperature, is shown. So, this is the equation log K is equal to minus 5040 E I upon capital T plus 5 by 2 log T minus 6.50 log G M positive into G E minus upon G M, where E I is the ionization potential of the metal in electron volts, G is the statistical weight of the 3 species, and the final terms become 0 in case of alkali metals. This term, this final term, this is 0 in case of alkali metal, and its value is 0.6 in case of alkaline earth metals. The degree of ionization of a metal is strongly influenced by the presence of other ionizable metal in the flame. If a metal X is present in the flame, so this X is also in equilibrium with X positive plus the electron, the degree of dissociation decreases due to the common ion. The common ion in the above case, just recall, M is in equilibrium with M positive plus electron, and in this case we have X is in equilibrium with X positive and electron. So, here the common ion is E, and due to this presence of this common ion electron, the degree of ionization decreases. So, we have less amount of metal present in M positive form. Now, coming on to the spectra of metal in flame. 3 types of spectra are there. The first is the line spectra. Flame excitation of many elements give rise to a line spectra which are less complex. Only lowest energy resonance lines of atoms has the sufficient energy which is useful for analysis. The characteristic of line spectra arises from the relatively low excitation energies. The advantage of line spectra is that it permits the use of low dispersion monochromators and filters and reduces the interference from overlapping spectra. Non-linearity in calibration curve sometimes obtains in the line spectra due to self-absorption. What happens? We have a straight line in the line spectra, and at high concentration or at very low concentration, this straight line, it deviates from its path, and we have slightly S-shaped curve. At the high concentration and low concentration, the straight line, it is what we call, it is not straight anymore. This is due to self-absorption. High concentration causes negative deviation from straight line, therefore, a S-shaped curve is obtained. Linear relation is obtained only for intermediate concentration. So, at intermediate concentration, we have a straight line. Second is the bend spectra. The bends originate from the excitation of metal oxides and hydroxide. Nearly 1/3 of the element, including rare earth and alkaline earth metals, have been determined using bend spectra in flame photometry. The third type of spectra is the continuous spectra. The presence of high concentration of some metallic species increases the background continuum. The reaction of the type M positive plus electron gives M plus H nu. This gives rise to emission, where the frequency of the radiation varies because the free electron in the flame have infinite number of kinetic energy. Coming on to the effect of organic solvent on flame spectra. The use of lower molecular weight alcohols, ketones, esters alone or mixed with water causes the enhancement of line spectra due to several effects, like number 1, low viscosity and surface tension causes higher rate of flow of sample into the flame. Second, cooling by the solvent is lessened. And the third is the combustion of the organic solvent contributes to the flame temperature. That means the flame temperature rises. Organic solvents increases the sensitivity, but interference also increases. So, the plus point of using organic solvent is the sensitivity, and the negative point is the interference also increases. Coming on to the instrumentation of the flame photometer. First is the sample delivery system, second is the source, then we have monochromator, detector, readout system. This is the schematic representation of a flame photometer. In this beaker we have analyte solution. So, this is moved to the mixing chamber. Here the oxidant and the fuel gas also comes and they are mixed with the analyte. So, this goes into the flame, then we have a filter or a monochromator, it goes to photodetector and finally to the amplifier or the readout device. First is the sample delivery system. This is the first component of the instrumentation part. There are three components for introducing liquid sample. First is the nebulizer. A nebulizer breaks the liquid into small droplets. We have different type of nebulizer, among them pneumatic nebulizer are the most commonly used. We have then aerosol modifier. It allows only smaller droplets than a particular size and removes the larger droplet from the stream. Then we have flame or atomizer. It converts analyte into free atoms. So, this is the overview of the process. We have ions in solution, this undergoes aspiration and the aerosol is formed. Now, this aerosol on vaporization in flames, we obtain a molecule. The molecule is made up of different atoms. Now, this atom, these molecules, these undergo dissociation due to the heat of the flame, and we have atoms which are present in the ground state. Now, the electron from the atom on heating, it gets excited to the higher level. So, this is the excited state. Now, when this electron it returns to the ground state, the energy is emitted in the form of light. So, this is the overview of the complete process of flame photometry. Next is the source. It is a burner which is used to spray sample solution into fine droplets. Flame is produced by a burner and the fuel plus oxidant combination, which includes premixed, Maker, total consumption, Schilder burner and nitrous oxide acetylene flames. Premixed burners. These are widely used because it maintains uniformity in the flame intensity. Aspirated, sample, fuel and oxidant are thoroughly mixed before reaching the burner opening in the mixing chamber. The second type of burner is total consumption burner. In this case, the fuel uses hydrogen gas and the oxidant is oxygen gas. Sample solution is aspirated through a capillary by the high pressure of fuel and oxidant at the tip of the burner. In this total consumption burner, the entire sample is consumed. Next part is the monochromator. Monochromator is nothing but different type of prism or grating are used. It is made up of quartz material which is used for making prism as it is transparent over the entire region. Grating is a series of parallel straight lines cut into a plane surface. Then comes detector. Detector is the photomultiplier tube, or it can be photoemissive cell, or it can be photovoltaic cell. Mostly the photovoltaic cell is used. It has a thin metallic layer coated with silver or gold which acts as electrode. Two layers are separated by semiconductor layer of selenium when light radiation falls on the selenium layer. A potential difference is created between the two electrodes which causes the current to flow. The next part or the next component is the readout system. It displays the absorption spectrum as well as absorbance at specific wavelength. These includes meters, charts, recorder and digital display. Nowadays, the instruments have microprocessor control electronics that provide output compatible with the printer and computers, which minimizes the operator error in data transferring. Coming on to the applications of flame photometry. The first is qualitative estimation. Flame photometry is used to estimate alkali and alkaline earth metals like sodium, potassium, lithium, calcium, magnesium, strontium, barium, etc. Detection of a radiation of a characteristic wavelength indicates the presence of a metal in the sample. This is also used in quantitative estimation and also used in the determination of metal ions in the sample of serum, urine and other body fluids. Flame photometry is also used in the determination of lead in petrol. Another use of flame photometry is to study the equilibrium constant involved in ion exchange resins. Flame photometry is further used in determination of calcium and magnesium. These are the alkaline earth metals in cement. So, these were the applications. Now, coming on to the advantages of flame photometry. The technique of flame photometry is simple quantitative analytical test based on the flame analysis. It is inexpensive and the determination of the elements such as alkali and alkaline earth metals is performed easily with most reliable and convenient methods. It is quite quick, that means less time is used, convenient and selective and sensitive to even parts per million, that is ppm, and parts per billion, that is ppb range. So, the sensitivity is up to ppm and ppb level. It has some limitations also. The limitation includes, firstly, the concentration of the metal ion in the solution cannot be measured accurately. So, what type of metal is present, we can easily come to know that what is the element present, but its amount or its concentration is not measured very accurately. Second, a standard solution with known molarities is required for determining the concentration of the ions, which will correspond to the emission spectra. Next is the information about the molecular structure of the compound present in the sample solution cannot be determined. Next limitation is the elements such as carbon, hydrogen, halides cannot be detected due to their non-radiating nature. Next limitation is limited number of elements can be analyzed using flame photometer. Mostly alkali and alkaline earth metals are analyzed using this technique. The sample requires to be introduced as solution into fine droplets. Many metallic salts, soil, plant and other compounds are insoluble in common solvent, hence they cannot be analyzed by flame photometry. Since sample is volatilized, if small amount of the sample is present, it is tough to analyze by this method, as some of it gets wasted by vaporization. So, we require a large concentration of the analyte, then only it can be analyzed. Further, during solubilization with solvents, other impurities might mix up with the sample and may lead to error in the spectra observed. So, these were the limitations of the flame photometry. So, that is all about flame photometry. Coming on to the summary of today's lecture. Today in the flame photometry, we have studied the introduction, the principle, the chemical reactions in flame, ionization in flames, spectra of metals in flame, effect of organic solvent on flame spectra, instrumentation, the applications of flame photometry, the advantages and limitations of flame photometry. So, in the upcoming lecture, we will be studying the atomic absorption spectroscopy, which is also called AAS, and ICP, induced coupled plasma. Thank you.